This is the presentation on section 15.1, what are solutions? We'll be looking at solutions here today, looking at part of the mixtures. We're going to be looking at some of the heterogeneous mixtures later on, including suspension and colloids, but that's coming up later. We're going to stick with the solutions with this lecture, also called homogeneous mixtures. A couple of key terms that we have to go over. First off, first one is solvent. That is the substance that dissolves a solute to form a solution. So we have a solution, which is one thing. It's the same throughout. Recall from previous chapters. Same throughout, top, bottom, middle, bottom, left, right, doesn't matter. Take a sample from all areas, it's going to be exactly the same. So the solvent is what dissolves something to form a solution. I like to use the example of Kool-Aid. When you make Kool-Aid, you have some water, you add some sugar to it, you add the flavor packet. In this case, the solvent would be water when you're making Kool-Aid, because that's what dissolves everything else. A solute is a substance that is dissolved. And again, in the case of Kool-Aid, this would be your sugar and your flavor. So those are the two things that are dissolved. Those are the two solutes. So let's take a look at solutions. Our formal definitions. It's a homogeneous mixture. The previous case we had was liquids and solids combining, but it can also be gases. If you look on page 454 of your books, it gives you some examples using all of these states of matter, solids, liquids, and gases. If you look for a solution, air that we breathe is a solution. It contains nitrogen at about 78%, oxygen at about 20%, argon at 1%, and a variety of other different things. That's a solution, mixed, several things mixed together. Soluble, another term that we can think about. Soluble is a substance that dissolves in a solvent. If something is soluble, that means it dissolves in it. Sugar is soluble in water. So here we have a solid and a liquid. Insoluble, a substance that does not dissolve in a solvent. We can look at sugar again and oil. If you've mixed sugar and oil, nothing will happen. It's just going to sit there, do nothing. It's not going to dissolve. So mixing solutions. Miscible is another term that we need to look at. For this one, the whole key here is when two liquids is the key term there. Two liquids can dissolve in each other at any amount. The larger amount will be the solvent. So if you take water and alcohol, that is one example of this. You can take any amount of water and any amount of alcohol, mix them together, and they will mix. Again, whichever one is in there at the most, that's going to be the solvent. Immiscible means two liquids are insoluble in one another. Again, they have to be two liquids. And an example here would be oil and water. You can mix those two together, shake them up, they'll separate out. They are immiscible. They will not mix together. So we have soluble and insoluble, talking about solids being dissolved in liquids typically. Miscible and immiscible, always two liquids. Miscible meaning they will mix. Immiscible meaning they will not mix. Solvation. Solvation is the process. That's a key word here. The process of surrounding solute particles with solvent particles. This is how things dissolve in something else, in a solvent. That's how the solute dissolves. Key term to remember, key phrase is like dissolves like. That's what scientists use to describe the solvation process. Polar dissolves polar. If you have a polar molecule like water, it is going to dissolve polar compounds, like most of our ionic compounds are going to be polar. So water is going to dissolve polar ionic compounds. Sugar is a polar compound, contains some oxygen hydrogen bonds in there. So that's going to make it polar, and so water will dissolve that. Nonpolar dissolves nonpolar. So oil and gasoline, those are a couple of liquids there. They are miscible. Those two are miscible together because they are both nonpolar. There's a short video clip. I can't show it here because of the technology. But what it does show is what this picture is, where you have your water molecules. All these water molecules here, what they will do is surround the ions. Here we have some sodium chloride, big chunk of it. And when you put that in water, those water molecules are going to surround all the ions. You will notice that if you have the chloride ion, the Cl, which is a negative charge, all these positive ends, these hydrogen ends, those are all positive hydrogen atoms on there, and they're going to be surrounding the negative chloride ion. Opposite is true for the sodium ions. The sodium ion is going to be positively charged, and so what's going to happen is the negative end, the oxygen end of the water molecule, will be surrounding that. So you can see it's totally surrounded to pull it off of this big chunk of sodium chloride. And that's how things dissolve. Solutions can be either aqueous solutions of ionic compounds or molecular compounds. Ionic compounds being like your sodium chloride, the table salt, potassium nitrate, whatever it might be, a lot of different ionic compounds. Same thing with molecular compounds. Molecular compounds are going to be your sugars, things like that, things that are not ions. So what determines how fast something will dissolve? There are a number of factors that determine that. Number one is agitation. When you're dissolving something, like for example sugar, if you're dissolving sugar in water, you mix it up, you stir it up, it dissolves faster as opposed to just letting it sit there. Temperature. The higher the temperature, the faster it will dissolve. When I make Kool-Aid myself, I don't add cold water to it and a bunch of ice and then try to dissolve the sugar. What I like to do is add some warm water, just a little bit of warm water, put the sugar in there, put that flavor packet in there, mix it up. It dissolves very, very fast. So once you get that sugar dissolved, that's when I add my ice to it. I add my cold water to that, mix it up, and I have ice cold Kool-Aid that I can make very, very fast. But that's the whole key, is that it dissolves a lot faster in warm water. If you try to put it all together in the cold water, put it all in there initially, and it takes a long time for that sugar to dissolve. Surface area of the solute. Again, the solute is the solid stuff, the sugar. The more surface area you have, the faster it's going to dissolve. So if you take sugar crystals, just a cup of sugar, put it in there, it's going to dissolve pretty quickly. If you take sugar cubes, if you take a cube of sugar, there's not a lot of surface area on that cube, but there's a lot of sugar that's actually inside of that cube that's not in contact with the water, that can't dissolve. So the smaller the material, the more surface area you have. So that's key. So if you have a whole bunch of these small little sugar crystals, they're going to dissolve a lot faster than one big one. So reduce the surface area, or the greater the surface area, the more surface area, the faster it will dissolve. You're going to be responsible for knowing these things, how to dissolve things faster. And again, I like to use my Kool-Aid analogy. Um, you mix it, you stir it up. That's why you stir it. It goes faster in warm water, and then use small crystal sugar as opposed to sugar cubes. Solubility. Solubility is how much a given solute can dissolve in a given amount of solvent. That is what our definition of solubility is. It can be expressed in a couple of different ways. Grams of solute in 100 grams of solvent, or grams of solute in a liter of solution. That's typically going to be for gases, because we're talking liters of a solution. That's when we're talking gases in the gas laws. So that's what solubility is. There is a solubility chart that we can look at here. Here's our solubility chart. This shows how different things, or how much of different things, can be dissolved at different temperatures. On the side over here, we have the solubility. The units are in grams of solute in 100 grams of water. A lot of times we talk about solubility graphs, we talk about in water, because water is the universal solvent. So here we have grams of solute in 100 grams of water, and on the bottom side here, temperature. On one of the previous slides, I talked about temperature. The higher the temperature, the faster it will dissolve. Higher the temperature, the more it will dissolve typically. You can see these lines. They typically go upwards, have an upward trend. The higher temperature, the more it will dissolve. You can see from the different compounds. Here we have calcium chloride and potassium chloride and sodium chloride. Each of those particular materials will have a different solubility. They all can be dissolved in water, but at different amounts and at different rates. And it also varies with the temperature. Some of them at higher temperatures, like calcium chloride, the graph really goes up sharp. The other ones, like sodium chloride, just a pretty much steady line, pretty flat actually. So that's what we're talking about when we're talking about solubility. This is how much can be dissolved. Let's say, for example, we have sodium chloride. At 80 degrees Celsius, we look at the chart, that's going to be that point right there. We move across, and it says that we can dissolve 40 grams of sodium chloride in 100 grams of water. So if we have 100 grams of water at 80 degrees, we can put in 40 grams, and that is going to form a solution. And that solution, if we go back to our PowerPoint here, cover this solubility. That's going to form a saturated solution. That is the maximum amount of solvent that can be dissolved in a given maximum amount of solute that can be dissolved in a given amount of solvent at a specific temperature and pressure. So that line that was formed there, think back at that line, that 40 grams, that is what can be dissolved, the maximum that can be dissolved, and that is a saturated solution. So when you have that happening, if you add some more to it, you're going to have a dynamic equilibrium between solvation and crystallization. Solvation is, like we had before, the definition, solvent surrounding the solute particles. Crystallization is that solute going back onto the crystal. So what's going to happen on a saturated solution, you're still going to have things dissolving, but you're also going to have other material recrystallizing, and that's going to be at the same rate. An unsaturated solution is a solution that is able to hold additional solute. If you think back at that chart that we had, that graph, anything below the line is going to be an unsaturated solution. A supersaturated solution, on the other hand, is going to be above the line. So that is when a solution has more solute dissolved than is theoretically possible. And in order to do this, what happens most of the time is that you increase the temperature of the water. When you do that, you can typically dissolve more material in there. And that's what you do. You keep on adding more and more. You dissolve a lot of material in there. And then when you start cooling the material down, sometimes it does not crystallize back out. It stays in solution. So you end up with a supersaturated solution. So what factors affect solubility? We talked about temperature. Typically, the higher the temperature, the greater amount that you can dissolve in there. For temperature, this will affect solids, liquids, and gases. For pressure, pressure will also affect the amount that is that solubilizes. This is typically just going to affect gases. The higher the pressure, the more solute can be dissolved in that particular material. We use that when we make soda pop. If you put it under pressure, have some carbon dioxide in the area above the liquid there, you put it under extreme high pressure, that forces the carbon dioxide into the solution. So at a greater pressure, you're able to put more carbon dioxide into that soda. Let's take a look at temperature. Solubility of solids typically increases with an increase in temperature. In some cases, it's the opposite. If we look back on our graph here, you can see in most cases it does go up, but in this one case of cesium sulfate, it does go down. It does go down with that particular temperature, or with temperature. Solubility of gases decreases as the temperature increases. So when the temperature increases, you can dissolve less materials in there. This is what happens during the summer. I love to fish. This is what happens in lakes, where the oxygen, the dissolved oxygen in the lakes that the fish use to survive, decreases on hot summer days. You get that water temperature up really high, really hot. It can hold less oxygen, and so that oxygen leaves the water, so the fish have less water, or excuse me, less oxygen to breathe, and then you might get some of these fish kills because of that. Here's a question that you might see. We'll go back to our diagram here in a minute. If you had a saturated solution of potassium chloride, so we have potassium chloride at 70 degrees Celsius, and it is cooled to 10 degrees Celsius, making a supersaturated solution. If you dropped in a seed crystal, what this means is if you have a supersaturated solution, in order for that extra material to crystallize out, it needs something to crystallize onto. And what a seed crystal is typically just going to be some of your material, potassium chloride in this case, that you put in there. Then the material that's in there at the too high of concentration, the potassium chloride, then it'll start to crystallize out. So if you drop in a seed crystal, how much potassium chloride would have to crystallize out to make it a saturated solution again? So potassium chloride starting at 70, going to 10. Let's take a look at our diagram here. Again, our PDF. We have potassium chloride at 70 degrees, going down to 10 degrees. And here's our potassium chloride. So let's take a look. If we have potassium chloride at 70 degrees, it's going to be that point right there. We move across, it'll be about 48 grams. 48 grams of that solute can be dissolved in it. If it goes down to 10, this yellow line here is that point right there. Looks like that's about 31 grams. So originally, it could hold 48 grams. Now it can hold 31. So if we just subtract those two, we get 17 grams is what is going to crystallize out to make it a saturated solution again. We need to get back to that point. That line, remember, is the saturated. Saturated is right on that line. Super saturated is above the line. And unsaturated is below the line. Be careful when you're talking about this, saturated, supersaturated, and unsaturated, that you're talking the same material. Because a point right here could be unsaturated for potassium chloride, but it could be supersaturated for sodium chloride. So it just depends what material you're talking about. So keep that in mind. And this concludes our presentation on section 15.1.